Irrigation of landscapes is a big subject. Those topics covered underneath the idea of landscape irrigation include design aesthetics, plumbing, plant biology, climate. All of those topics you need some information about those to be able to create a really efficient and appropriate landscape irrigation system. We'll touch on each of those in this lecture, and this lecture is supposed to just give you an introduction to some basic landscape irrigation systems. You might already have a good knowledge about systems like that, and that's great, but if you don't, we'll introduce the subject of the basics here for you to get ready to design, install, and maintain a basic landscape irrigation system. So, as mentioned previously in lectures, we are trying to maximize the performance of our plants by providing them with all the things that they need in our landscape. As far as irrigation goes, we're managing soil moisture and the moisture inside the plant too. So the plants do what we want them to. You can call that peak plant performance if you want, but it provides the plants with the optimum amount of water, not too much and not too little. How do you know if they're getting the right amount? Well, one is taking care of your plants personally and looking at them, touching them, feeling them, and deciding are they under water stress or not, or under overwater stress. You can also look at charts and formulas that tell you how much water a plant needs based on the climate you're in, the microclimate, the species type, the soil type. There are ways to do that, so kind of like reference materials. You can also use soil moisture sensors, and that's something that reads the soil moisture continuously and can tell you if it gets too dry or too wet. So our business as landscapers is mostly aesthetics. We want things to look good and perform well, production, like as in an athletic turf. Then a landscape is more of a giving us what we want out of it, or fruit trees and things that produce food. So we want to enhance that too in landscaping. Some background information. As you know, water is needed in the photosynthetic process. The plants use photosynthesis to make sugars from CO2 from the air and using water drawn in through the roots. Plants absorb water through root hairs, small extensions of the outer epidermal layer of the roots that increases the surface area of the root. And the process is osmosis, how the water and the nutrients carried in the water get into the plant. If there's too much water in the soil, the roots will suffocate. Roots need oxygen. They are doing cellular respiration, which requires oxygen, but they also need water. So you need, again, not too much water, but some water. But not so much that all the pore spaces are filled with water. You need some air pockets in there too. So if the soil has too much water, it's not good. But if there's too little water, the soil is too hard and it gets compacted and roots can't push through it. Okay, how is water lost from your landscape? Through two processes. Transpiration, that's water that's being evaporated out of the leaves from the inside of the plant in the xylem, the tubes that carry the water from the roots to the leaves, from the inside into the atmosphere. So transpiration is the loss of water from the inside of the plant into the atmosphere. Evaporation is water loss from everywhere else, meaning it could be water loss from the soil or rocks or your deck or patio, or water loss from even droplets on the outside of the plant evaporating into the atmosphere. That's different than water coming from the xylem out through the stomata in the leaves into the atmosphere. That's the second one I mentioned, is transpiration. And water loss from the surface of the soil and all other surfaces is evaporation. Together, they're called evapotranspiration, or ET, and that's the combined water loss of both. It's measured in inches per day usually, or inches per week, or inches per month that is evaporating. And the ET rate, so the rate at which that water is being lost through ET, is affected by sunlight, temperature, humidity, wind, precipitation. You can imagine on a hotter, windier day, more evaporation is happening, more transpiration, more evapotranspiration. One example of how ET rates change easily comes from the video linked there. the bottom of this slide. Winds as low as 5 miles per hour can increase the ET rate by 20%. Winds as low as 15 miles per hour can increase the ET rate by 50%. And daily fluctuations also occur in ET. You might have noticed, maybe you've noticed, but in creeks they flow higher and more at night because transpiration, the plants growing in the creeks aren't sucking the water up and transpiring it. That whole process shuts down. Plants are needing and using water during photosynthetic processes, which is during the day when the sun's out. So when the sun goes down, photosynthesis slows down and shuts down, and they don't need as much water, so they're not drawing as much into them, into their roots and into the body of the plant. Thus, if the plant is living in a creek area, a lot of the water is being sucked out by the plants during the day and not at night. Midday warmth can cause closure of the stomatal pores, the leaf pores, where the water can evaporate out in transpiration, and cause a decrease in transpiration. Just by the heat of the day, plants sometimes they're trying to balance out, like let the pores, the stomata are open to let CO2 in for photosynthesis, but not too much water out, because that's not good for the plant to lose too much water too. So if it gets really hot, they sometimes will do photosynthesis kind of in the morning as the sun comes up until midday, but then once it hits a certain high temperature in the midday, they close their stomata. So even though they're shutting down the ability to let CO2 in, they're minimizing water loss at the same time. In this image, precipitation indicates water that enters your landscape from not just from rain, but also from your irrigation systems. Even water running onto your property from creeks, rivers, or runoff from your neighbor's overflowing irrigation system. So precipitation means all water entering your site. And often when you're talking about irrigation systems, precipitation means what comes out of your sprinkler or emitter system. So it's not about rain from the sky. So how do you know if your plants are under water stress? That's one way you're figuring out if your irrigation system's doing its job. They will look dull in appearance. The older leaves will fall off. The leaves will be wilting. That's signs of water stress in your plant. And that can be caused, as I said earlier, by low humidity, really dry, hot winds like our sundowners and Santa Anas, or high temperatures, day or night, intense sunlight, or mechanical injury, like a gopher chews off a bunch of roots. That's going to cause the plant not to get enough water, and it'll show water stress. I've seen whole plants, I'm thinking of artichoke plants right now, that looked great one day and the next day just falling over completely because a gopher chewed off most of its roots. And when a plant is under water stress, it is not doing its photosynthetic process as well. It doesn't grow as fast, it's more prone to disease, it looks worse, produces less. All of those things are negatives for us humans who want what we want out of our landscapes and production out of our plants. So some basic principles of water application in an irrigation system. When we irrigate, we are replacing the water that's been lost due to ET and possibly to runoff. Is watering every day the best for plants? It depends on the plant. Some plants like to have their feet or their roots stay moist. Ferns and camellias, things that like shadier, cooler climates with richer, more acidic soils. But some do not. In general, it's better to let the soil dry out between waterings, between the application and the shrinking and swelling of the soil that comes with the wetting and drying of the soil. Helps the structure of the soil stay healthy, keeps it open, more pores for air and water to get in and microbes to inhabit. It's better for it. So enough water should be applied to encourage deep rooting. You want roots to grow deep, so you have to leave the irrigation system on long enough so water soaks down and infiltrates deep into the root zone and even below where you want the roots to grow into. But not so much water that it's soggy and that water sits on the roots causing root crown rot, something like that. That's not good either. So it's better to do it every few days or once a week, longer periods, than a little bit every day. Now turf or lawns usually require more of like a 3 times a week, 15 minutes kind of thing. So those roots aren't as deep and they can take a shorter irrigation system running multiple times a week, and that's okay. So shallow irrigation, a little bit every day, encourages shallow roots overall. Again, that's okay for lawns, but not for your perennials, shrubs, and trees. And the other thing that you need to know about is distribution uniformity. The application of the water from your irrigation system should be even across the whole landscape in general. Now, we're not talking about drip systems where you have emitters right at each plant, but more overhead rotors or rotators or sprinklers, like for lawns and areas where your system sprays the whole square footage. That water should be distributed evenly. Let's talk about sprinkler system design now. So we've said plants need water, but not too much or not too little. Where does the water come from? To irrigate your plants, it can come from precipitation from the sky, from rain, but it also can come through precipitation from your irrigation system. It can come from your well that you have drilled on your property, or from your water district or municipality. How does water get to your property? Water flows from the city water, or wherever you're getting your water from, in pipes by pressure, pump or gravity pressure, and that pressure varies and must be considered when you're designing the irrigation system. You have to have proper pressure for certain systems and certain emitters and sprinklers. The emitters are the small devices on an irrigation system where the water exits the pipes and goes onto your ground, and onto the plants. That's what an emitter is. It could be a pop-up sprayer, an overhead sprayer, a micro sprayer, a drip system. All of those things are called emitters. And each of those emitters has pressure requirements, water pressure requirements. Those will not work properly unless you have the proper pressure. So the bad news about irrigation systems is you have to know basic hydraulics, which is the study of liquid moving in confined spaces under pressure, like water moving in an irrigation system, to be able to properly design that irrigation system. That involves calculations. Hydraulic calculations need to be made to figure out the flow rate, the pressure, and how that changes in your system to make sure your emitters will be functioning under the proper pressure for them to work properly and give the plants the water that you are expecting and that the plants need. Save the good news for last. The good news is if the elevation change from the lowest to the highest point in your irrigation system, or even just a single valve, is less than 7 feet, you don't have to worry that much about pressure in that system, if it's not too large of a system. Smaller residential systems that don't have big elevation changes within that irrigation system, you don't really need to worry about the pressure changes. It'll be fine. But if elevation changes are greater than 7 feet within your irrigation system, you do need to consider the design and do the calculations with pressure to make sure that your emitters are functioning under the right amount of pressure. Over 3 psi, or pounds per square inch, change can alter the functioning of the emitters and possibly make the plants receive inadequate water. Two types of pressure to know about as far as water and irrigation systems is static water pressure, when the water is in the pipe but it's not moving, like the valve is closed, so your irrigation system is not on and the water's just sitting there, but it is under pressure. That's static water pressure. Then your valve opens, or your hose spigot, you turn it on, water shoots out. That's dynamic water pressure. So the water is moving now and it still has pressure. That would be the dynamic water pressure, water in motion. Now let's talk about a hypothetical irrigation system as an idea, an example of how to calculate water pressure throughout a system and how it changes due to the system itself. And it's an example of calculations you might need to go through to figure out if your system is going to function properly. So let's analyze pressure in a hypothetical irrigation system. Water's coming from the street through the main line, which comes from the city of Santa Barbara in this made-up example. The water branches off the main line in a lateral line, a PVC pipe underground, where it goes to a valve that then goes to 2 pop-up sprinklers to water your lawn. So this is a very simplified irrigation system. Let's say the water pressure is coming out of the main line at 70 psi. So the city of Santa Barbara pressurizes the water, and it also has some gravity pressure to it, but it's coming with 70 pounds per square inch to your property. So that's what it has when it starts into your irrigation system. Let's pretend your house is downhill from the street. So you drive up your street and then you turn off into your driveway and you go down the driveway down to your home and the lawn, and that is a 20-foot elevation drop. That's what we're going to say in this hypothetical example. So what will the water pressure be at the valve at the bottom of your driveway? Before it goes out to the pipes that take it to the emitters and to your lawn, it's just at the valve. So it's gone from the street down your driveway to the valve. So the valve will be greater than 70 psi because the water has gone downhill. There's been an elevation change, 20 feet elevation change. So there's a 20-foot column of water inside the pipe pressing down on the valve. It's similar to you going down in a pool 20 feet or just 10 feet. You'll start to feel pressure, more and more pressure on your ears because there's a greater amount of water above you pressing down on your ears. So as irrigation systems decrease in elevation, the pressure inside the pipe in that descension will increase. So as the pipe goes down, water pressure inside the pipe increases about 0.5 psi per elevation foot drop. And if the pipe goes uphill, the psi drops about a half a psi. It's actually 0.433, but we're using 0.5 rounded just to make it simpler. So in that 20-foot drop in elevation, for every foot, the water pressure is increasing 0.5 psi. So your water is actually going to be 80 psi by the time it gets to the valve. Here's a little drawing or diagram. So you have water pressure that's 80 psi at the valve. So it's not as simple as what I just said. There's also changes in the pressure of the water due to a few different forces. One is the elevation changes I just told you about. That's number 3 here on this slide, but also frictional losses of pressure. So inside your irrigation pipe, the inner surface of the pipe is not absolutely smooth. There are microscopic rough areas. It's rough. So the water moving along in the pipe will slow down and lose pressure just because the pipe itself kind of slows it down. It's friction of the water against the inside of the pipe. So that can cause pressure losses. Also water moving through the valve itself, or regulators, backflow devices. If your irrigation pipe does a 90-degree turn, that slows the water down and decreases the pressure. All of those things can cause changes in pressure in addition to the elevation changes. This is a page from a printed, published chart. You can usually get these free at your irrigation supply store. And they're used to calculate the frictional losses of water in irrigation pipes per 100 feet of pipe, depending on the diameter of the pipe, which are listed across the top of that chart. And then down the left side, on the left, vertically are listed the flow rate, gallons per minute. And if you put those two things together, it shows you how much psi is lost per 100 feet of piping, and that can help you figure out the pressure change. On the outside of the emitter packaging, the emitters are the things that release the water. In our little diagram, those two blue things, they're like little sprinklers in the lawn. On those emitters themselves, or the packaging, it says the pressure range under which those emitters function properly. So that's something you can plan on, and that you'll want to figure out, is there enough pressure when the water gets to that emitter or that sprinkler for those things to function properly. So in this example, the pressure emitters are receiving 72 psi, which is way over the 30 to 45 psi range. So these emitters are not going to be functioning properly, and you'll need to put some kind of pressure reducing device on there so it's getting the water pressure down to 30 to 45 psi. Or you would change the emitter, the sprinkler heads, out to something that can handle higher psi. But let's look along the bottom here, and you can see kind of a review. At the main line, the water in the irrigation system was 70 psi. That's what the city gave it to you at. Then as it dropped 20 feet in elevation, it gained 10 psi, so now it's at 80. Now here you see at the beginning of the valve it says 80 minus 1.5. Well, we subtracted 1.5 psi to account for the frictional loss of pressure in that 20-foot length of pipe. And then going through the valve, it loses a little bit more pressure, so we took off another 5 psi. So when the water is coming out of the valve, it's now at 73.5 psi. In that first 50-foot length to the first emitter, it loses another 0.75 psi due to frictional losses moving along in that pipe, and then another 0.75 in the second 50-foot length of pipe. So at the last emitter of this very simple system, it's receiving 72 psi. And as was said in the last slide, 72 is way too much for most emitters and sprinkler heads to work. So you need to install some type of pressure regulator that can decrease the pressure. It can increase it too. It regulates it up or down. You can see there's 3 examples here. These are installed above or below ground in your PVC pipe. They can do either. They come with preset outlet pressure, so whatever pressure is going into it, they'll come out at 30 psi or 40 or 50, whatever. And you can get the 3/4 inch or 1 inch female threaded inlet and outlet, and they have operating flow rates too that work for them, and operating ranges of pressure going in, so they can take up to sometimes like 100 psi. Going through this pressure regulator, it can come out at 40, and they will regulate that. So that's the way you deal with that last example. When the 72 psi was just too high for your sprinklers, you could put a pressure regulator on it and solve the whole thing there. If you wanted to change out those sprinkler heads to these sprinklers that have an emitter, a pressure range that was more appropriate for the heads you already have, you could change those out too. But it would be really easiest to just add pressure regulators. And this slide is just showing you, for example, a pressure regulator was added to reduce the pressure from 78.5 to 40 psi before the water went from the valve out to the 2 sprinklers, and the first sprinkler and even the second. So when it does hit those sprinklers, those emitters, now it's hitting 34 and 33 around psi, which means both of those emitters will function properly. Because remember from a few slides ago, the pressure range for those emitters was 30 to 45. So we used a pressure regulator to solve that whole issue. Check out these MP Rotors. So they're rotating pop-up sprinklers, mostly used for lawns, but also some garden beds too, where the water comes out in fingers that rotate of water, and the droplets are much bigger in these systems as opposed to the pop-up just spray kind of lawn sprinklers, which have little teeny droplets. The bigger the droplet, the less surface area, the less likely it is going to be affected by evaporation and float away. So you have a lot less water needed to be applied with these MP Rotors than you do with the traditional spray sprinklers. Will our example system work with MP Rotors? Yes, it will. Most MP Rotors have their pressure range like 25 to 55 psi, and that's enough. This system is giving around 33, 34 psi at these 2 sprinklers, so you could just change those out, and your new water conserving MP rotor or rotator heads will work just fine in that pre-existing system. Let me just give a little introduction to drip systems. Drip systems are the above ground, low volume irrigation systems that deliver the water to precise locations in low volume slowly over time. Although they don't actually drip anymore, some do, and all of the systems started out, 30, 40 years ago as just drip emitters. Water would just drip droplets out of these emitters slowly, and now we have lots of different kinds of emitters in drip systems. Lots of types of emitters that can deliver water to precise locations slowly. That's really what we're talking about now. So they're also called micro irrigation systems, but they're still known as drip. It reduces the evaporative loss of water, which can be caused by sprayers, which I mentioned in the last slide. So using the bigger droplets from the rotors and some of the new emitters, you really reduce a lot of water loss from the spray emitters. As far as efficiency of your irrigation systems, sprinkler systems are about 75% efficient. Drip systems, typically 90% or higher. And what does that mean? What is efficiency? It's just the amount of water that's emitted actually getting into the soil around the roots of plants. So that's all about evaporation. Evaporation from water between when it comes out of the emitter to when it hits the ground. So it's really just about evaporating out of the air once it leaves the emitter before it hits the ground. That's the inefficiency that we're talking about. And the drip systems are the preferred method of irrigation in the desert areas of southwestern United States and the landscapes all around the south coast of California and many other areas. And most drip systems normally operate below 35 psi. You don't want it to be too high above that, or the little tiny emitters tend to not function well or pop off. So you want it to be below 35 psi. Here's a picture of some common drip system materials. The upper left is a mix of different fittings and little emitters. Upper right is the drip line called polypipe. It's made of polyethylene and it's flexible. Because it's flexible, it can collapse. It's not meant to be stepped on or not meant to be underground. The image is showing you a no-no. You don't bury the polypipe underground. It can collapse. But it is meant to be on top of the ground with mulch over it. So it's right on the surface, emitting the water right next to where you want it to go. Not spraying everywhere, but just you have the emitters just where the plants are and just where they need that. That top picture is the classic drip emitter, the emitter that comes off that black poly pipe, and the water comes out of it very slowly and drips, just like you see a drop coming out. The upper right picture is like an inline emitter, right, that's plugged in right into the poly pipe. So it's right on the ground, right on that pipe, and water can come out of that at different flow rates. You can buy different emitters that emit certain rates of water. And then the bottom one is also a type of drip system or micro irrigation system. It's a little micro sprayer that can push water out in a wider area, often used for ground covers. A couple other examples of micro irrigation emitters. The shrubler on the left up on a riser, so the water can spray out in a little umbrella form in a wider area, and even a micro jet sprinkler. See those a lot in commercial orchards, including avocados here in the south coast of California. Often the valve, regulator, filter are all underground in an irrigation box, although they can be attached above ground directly to a hose spigot too, as in this case, which you see more often in an orchard or agricultural situation. But there's the basic setup of the components that go into controlling and setting up a drip system. Let's talk a little bit about selecting emitter or sprinkler heads. So the factors involved in selecting the right emitters are the size of the area you're going to irrigate and the shape, the water pressure, of course, the wind conditions, the types of plants, the flow rate, which is gallons per minute that's available, and then the slope too. Those will all come into play when you're considering what kind of emitter / sprinkler heads to use. This is a nice comparison of 3 different types of drip emitters. In A, we have a micro sprayer. B, we have a bubbler, which slowly bubbles water out faster than drip, but not as fast as a micro sprayer or shrubler. C is dual drip of inline emitters onto that same tree. And you look at the wetting zone. They both can get deep, pretty full wetting and infiltration of the water if left on long enough. And then below in D, you can see the differences of if we had the exact same emitter in 3 different soil types, how the wetting would be different. With sand, it's very porous and it doesn't hold on to water very well, so the water infiltrates very deeply, very quickly. In clay, it does not move very fast. It's denser and it holds on to water, so you get more lateral expansion of the water in the soil instead of vertical. And loam is kind of right in between. So here we've got a range of types of emitters that can be chosen from the non-drip, like the pop-up spray heads, the pop-up rotors, and drip systems like bubblers, shrubblers, etc., and the other ones we've talked about. Here's a question for you. What type would be the best to irrigate the outfield of a baseball field? Well, when you're dealing with large areas of turf like athletic fields or maybe big lawns on a campus or in an apartment or condo complex, the best thing to do is to use the pop-up type of emitters that will emit. They can cover a big area, and of the 2 listed here, pop-up spray heads and pop-up rotors, the rotors are going to be the one that's by far the most water conserving and have wide reach. And you can step on them too, because when they're done, they go back down. They pop up when they're filled with water and the pressure makes them go up, and when the valve turns off, they go back down and they're not a hazard. Of pop-ups and above ground irrigation systems that can cover large areas, you have pop-up sprayers on risers that come up, like I said in the last slide, with pressure. There's drip bubblers on risers too, so you can use drip systems too that have these up 6 or 8 inches off the ground, and then that little umbrella of water that's coming out of these goes to a larger area. Still not appropriate for like a lawn would be the bubblers, but you can use them for garden beds and ground covers. And then there's also impact heads on risers, the old classic rainbird type of sprayer, where the mechanism hits the water and it makes it rotate. So here's the question: what type of heads would be the most economical and efficient for irrigating several acres of ground cover? In this case, I would say an impact heads on risers. We're talking large areas. Now these ones like the pop-up sprayers and the impact heads on risers, they will have a lot of evaporative water waste. So that's something to think about. Of these 4 types of emitters, which one would be the best for small patches and strips of lawn area? So maybe something like the parkway between the sidewalk and the street, the curb. That would be a small patch and strip of lawn. What do you think? Well, it does depend what you're growing there, but we already said it's lawn. And in this case, I think pop-up spray heads that have a short range might be the best thing to use. How do you determine how much water is coming out of your irrigation system to know if you're putting the right amount of water back that was lost from ET? You can use a simple catch can test. These folks are setting up a catch can test. This is one that I was involved in this short irrigation course I took at Cal Poly. These small cones are set out in roughly creating a grid with the cones. We're just starting to put them out here, only 1 row. And then the irrigation system's turned on for about 10 minutes, and then it's turned off, and then you measure the height of the water in each of the cones, and you can average it. So what's the average amount of water that was applied by that irrigation system in 10 minutes? You can times it by 6 to get inches of water coming out per hour. You could use millimeters too if you wanted to. And then you schedule that system on to be the proper amount of time per week or month to apply the amount of water that you know from weather stations is lost due to evapotranspiration in that particular month. So you dial in those 2 things, your irrigation system to apply the amount of water that you know from weather data is lost through evapotranspiration. This is an example of a laminated irrigation chart, usually placed in the control or the irrigation control box, and it tells the landscaper where the irrigation systems are underneath the turf, and which valves in your system are covering which areas of that turf. That helps when there's a break for determining the precipitation rates for matching the ET rates. So you know if there's a break and there's a problem and not the right water's coming out. This can help you locate and figure out where to try to fix it. The catch can test is used to determine the irrigation system. Again, precipitation rate. In the irrigation system talk, we talk about what comes out of an irrigation system as the precipitation rate, how much water per time. Whereas weather data from the weather stations and websites like CIMIS, which is the California Irrigation Management Information System, is used to determine monthly ET rates. So an irrigation system should be scheduled to emit the same amount of water in a month that you know, or that you figure out evapotranspires according to the CIMIS weather data. And that's a start on the basics of irrigation systems.